Okay, in the last episode, we used AI to take over the RK3588, allowing it to read data sent from both the perception computer and the planning computer. From the actual results, you can see that the whole process is quite clear, straightforward, and easy to implement. The system can be fully taken over by AI, and it can quickly send the processed data out in real time. We also checked the ROS package and confirmed that the data flow was working properly. Yesterday, we mentioned a bigger challenge, developing our own drone ground station app without using QGC. We are not going to use any other ground station. Instead, we wanted to use AI to build a ground station within the shortest possible time. So let's take a closer look at how we actually made it work. I have already connected another AI tool, Codex, and asked it to help us write the ground station. The idea is to build a web-based ground station, moving away from the traditional app model and switching to a more flexible web-based approach. Web development usually includes both a front-end and a back-end. In our case, AI is especially effective when writing front-end code because it can quickly turn the interface design and interaction logic into usable pages. So before writing the actual ground station, our first step was to design a clear prototype. We designed the prototype of the AI ground station in Figma. You can also connect AI with Figma because Figma works very well with AI-assisted design and is ideal for quickly creating interface prototypes. Once the prototype design was completed and the interaction logic was clear, we gave the design link directly to Codex. After that, we linked Codex with Figma so it could read the prototype design and understand the interface layout. Based on the prototype design, it automatically generates the front-end code for the ground station. As you can see, Codex can complete the whole process by itself, including packaging, building, and uploading the code. More specifically, both the front-end service and the back-end service are running directly on the RK3588. The RK3588 reads the flight controller data, processes it through the back-end, and then forwards it to the front-end interface. In this way, on the Android ground station, we do not need to install a separate app. We only need to open the browser and access the web ground station directly. In the browser, we enter the address 192.168.1.66:5173 to open the web ground station. Then we can access the ground station through the browser. The data path is very clear. The flight controller first outputs real-time data, the RK3588 reads it, the backend running on the RK3588 organizes and forwards it, and the front end displays it through the web interface. In other words, the entire web ground station is running on this onboard computing platform, while the Android ground station only works as the display and operation terminal. After logging into the ground station we built from scratch, you can see that the data refreshes normally and the basic communication loop has already been established. Next, we connect the drone to the ground station. This is our latest FlyCore-01 and we'll use it to verify the communication and control functions. After clicking, we enter the ground station interface. Now, if I move the drone, you can see the attitude data appearing in real time. When I move it forward, both the x-axis and y-axis data change accordingly, and the attitude indicator also works normally. All of these interface functions were generated by Codex directly from the prototype design. So what functions did we implement in this first version? We now have basic displays for position, speed, attitude, heading, and flight controller feedback. So the main flight status can already be monitored in real time. It also supports core control actions such as arming, disarming, one-click takeoff, and one-click landing. Even though the development time was very limited, these essential ground station functions are already working properly. The entire AI development process for this ground station, including the actual coding and debugging, took less than 1 hour to reach this result. Later, we may continue to add more advanced functions such as route planning, mission management, and more complete flight operation logic. In the past, developing this kind of web-based ground station often required at least 6 months, and in many cases, it could take 6 months to a full year. But now, if AI is used properly and the system architecture is already well prepared, a solid and usable prototype can probably be built within just 1 week. After fixing bugs and polishing more details, a professional ground station could possibly be completed in about 1 month. Another key factor is that the interfaces in our FlyCore system are very convenient and easy to work with. Data forwarding is simple, and letting AI take over the RK3588 is also straightforward because the underlying infrastructure has already been built and fully prepared. Once the infrastructure is ready, you can build many similar functions on top of it simply by using your imagination and combining different modules. The development efficiency is much higher than before, and the whole process becomes much more flexible. This is the second challenge we completed. In other words, we used AI to develop a working drone ground station in a very short time, and the basic functions have already been verified. Now we will use this web-based ground station to control the aircraft. At first, we had a serious internal discussion about whether to build a web ground station or an app ground station. We compared both options from several perspectives, including development efficiency, cross-platform compatibility, deployment difficulty, and how well each approach could work with AI-assisted development. After discussion and team vote, we chose the web approach. In fact, we completed most of it in only half a day, which was much faster than we expected. Today, we will run a real flight test to see whether the web ground station can send commands properly to the flight controller, whether the drone can respond normally after receiving those commands, and whether one-click takeoff and one-click landing can work as expected during the actual flight. Okay, everything is ready. Now let's begin the flight test. Okay, it is slowly taking off. Let's move the sticks. Your data is also shown. Now trigger one-click landing from the ground station. Okay, the ground station interaction and the flight test have basically passed. First, it can read flight controller data and send arming, one-click takeoff and one-click landing commands to the flight controller. Command communication works properly. This proves that the ground station architecture we developed is fully workable and the core communication and control logic has been verified. Some details may still need improvement, but I believe that by continuing to talk with AI, correct it, and let it keep modifying and optimizing the code, we can eventually polish this into an industry-grade ground station in a very short time. That is the power of AI. In previous episodes, we summarized FlyCore's hardware and software architecture in detail. More importantly, we spent a lot of time showing how to develop FlyCore with AI tools in real scenarios. To make FlyCore more AI-friendly and easier for AI to understand and develop, we have done a lot of underlying work. First, we integrated the LQ10 video data link. It connects the onboard computer, planning computer, and flight controller into one communication path. They can access each other through the local network, connect to the internet when needed, and also be remotely taken over by AI for development, debugging, and control. This means AI can directly interact with the onboard systems instead of only generating code offline. Second, in the hardware architecture, we creatively proposed an innovative three-brain design: the perception left brain, the planning right brain, and the flight control cerebellum. The perception left brain focuses on understanding the environment. The planning right brain handles decision-making and path planning. And the flight control cerebellum is responsible for stable flight control. They are independent, makes the system more modular, but they can still communicate with each other to complete the perception, planning, and control loop. Third, for the system software architecture, we strictly follow a technical framework built around OODA, SDK, simulation, and AI applications. This allows each module to remain independent and clearly separated, while still working together under the same overall architecture. In this way, we achieve both strong decoupling for development and a unified structure for system integration. Fourth, we synchronize clocks and sensors across the three hardware systems. Previously, the flight controller used one time base, while the onboard computer used another. This caused many problems, including difficult engineering issues, unstable data alignment, and major deviations in the code logic. To solve this properly, we spent a lot of time and effort optimizing the system at the hardware level, so the different computing units could work under a unified time reference. Finally, this product took us 4 years to develop, from the early architecture design to continuous testing, optimization, and real flight verification. It has been flown every day on our BO1, and it has already gone through many real operating scenarios. It is also being delivered continuously to customers, but a system that has been validated in real applications. Today, we want to open this capability to more users. We hope more drone manufacturers, as well as our downstream partners, can build drones that are better suited to their own application scenarios and use this board set to improve development efficiency, reduce repeated engineering work, and shorten the time from prototype to real application. We also hope to work together with more partners to promote progress in drone technology. In the future, we will keep improving this system, iterating its functions, and expanding its application value. Today, this product is finally being officially launched. One more thing. This July, we will hold a hackathon in Chengdu focused on AI drones development. The theme is Build an AI Drone in 3 days. During the event, participants will work directly with our system and experience the full process of building an AI-powered drone. We hope everyone who is interested in AI, drones, low-altitude robotics can join this event. You can experience this system on site, work with the hardware directly, and see how an AI drone is built. Okay, thank you for following us and supporting this series. We will continue sharing more updates about FlyCore in the future. See you.